And in 8.5, we're going to be solving story problems. And you will need your calculator for this. Okay, so we're going to be working with exponential growth and decay functions. Your functions are either going to have f of x equals or y equals, or sometimes they might give you another variable. But the continuous exponential growth, okay, is almost the same equation as your continuously compounded interest. It's just that the output is y or f of x. The principal is a. Okay, so remember that a is your initial value. Your t is time. Okay, and this new variable k, that is used as either, well, we're going to start with growth. So this is going to be the growth rate constant. Sometimes it's just called the growth constant. Okay, and then one thing that we're going to focus on today in our notes and what you'll have to do on your homework if you want full credit is that you have to solve each one of these story problems with algebra. Okay, so we've gone over several ways to solve different equations this year. This whole chapter is about logs, and so you are going to have to solve using logs. Okay? And in particular, because we're using e, what is the inverse for e? Yep, the natural log. Okay? So today we're going to be using the natural log. Okay, so ln to solve. Alright, so example 1 gives you the initial population as 8,000 and says it grows continuously at a rate of 26%. You are going to write an equation that represents the rabbit population P in thousands after t years. Okay, so write an equation to represent the population P, and I wish I would have put like these commas here, in thousands, so P is in thousands after t amount of years. Okay, so your initial population A is 8,000. If it says that the population is measured in thousands, when you plug it into your equation, you actually want to divide that by 1,000 to get the value that you're going to use in the equation. So if they do give you a stipulation where this is in thousands and it's 8,000, you are going to simplify that. Okay, and then we are using the f of x equals ae to the kt, but it says the rabbit population is called P, so instead of f of x equals, we're going to use P equals. Okay, so we're going to use AE. Now the power is KT. Remember we talked about how these are similar to each other? So if they tell you that the rate is 26% per year, okay, yep, you're going to write it as a decimal. Okay, so if the rate is 0.26, that is also your value for K. And then you're going to leave that as T. So P equals AE. Okay, and that's going to be your equation. So whenever they ask you to write a model or an equation, okay, you always need your initial value and your constant K to make the equation. Sometimes they'll tell you what to find. Other times they will give that to you. But anytime they ask you to write an equation, you have to have these two things. Initial value and the constant. Okay, so example 2 has a lot of different directions in it. So we're just going to start with the given information. It says an experiment starts with 20 bacteria cells. Okay, so if it starts with something, that's the initial value. After 45 minutes, there's 710. They call this bacteria A. There's going to be a bacteria B. So when it says to write the equation that models the number of bacteria, okay, we are going to have to make sure we know the initial value and the constant. So this says the number of bacteria cells Y after 2 minutes. So we're going to have Y after T minutes. Alright, so then looking at our model, we're going to plug in our values. So we know that A is 20. So this is organizing our information. We know A is 20. And then we also know when T is 45, there's 710. What would that go in for? Y. So when T is 45, Y is 710. So what we have to do is we have to use that to find K. Okay, so they will give you enough information for you to find this constant of growth. So we can plug in 710 equals 20 E to the KT, so 45 is T, and then we're going to solve. Okay, so if you were here with me with 8.4, we solved equations that were similar to this. So you have to find a way to get the exponent E by itself, or not the exponent, the exponential function E by itself. And to do that, you're going to first divide both sides by 20. So dividing by 20 is going to isolate the E on this side. Remember, leave a little bit of space there. K times 45 is just 45K, so you can rewrite it like that. And then you can choose if you want to simplify or not on this side. If I see the zeros on the end, I'm automatically going to simplify this. And you really could cut that in half and use the decimal. That's fine too. Now, do you guys remember from last week what undoes E? Yeah, the natural log. Okay, so we're going to take the natural log of both sides. Natural log is ln. That is how it's written. And the natural log and E are inverses, so those are going to undo one another. And we're able to bring that exponent down. Do you guys remember why we're able to do that? Yeah, what's that? Do you guys remember what the rule's called? Yep, your power property. Good. So that comes down in front. And then all we have to do now to solve for K is divide both sides by 45. Okay? When you are finding K, generally they'll either round to the nearest 10,000th or 100,000th. It depends on what you have. So in other classes, have you guys talked about significant figures? Yeah. So if you have a 0, okay, then generally they'll go to 5 places. And then if you don't, they'll go to 4. Okay? So if we do the natural log of 71 divided by 2, you can either press enter there, or you can also do that all at one step. Okay, so would that be right to say that if I did 0.07932, that would be 4 significant figures? And that's just a good general rule to use. Okay, if they don't tell you what to round to, then usually we use 4 significant figures to round K. For part C it does, yep. For your K value, it will be at least 4. Yeah. Yep. Okay, now remember what we're doing is what they asked us to do in part A is to write the equation. So an equation is the same thing as a model. It's modeling the situation. Okay? So it tells you y, so we're going to use y equals. Your A value is still 20. Okay? Your E is going to be the exponential function, and then it's 0.07932 t. Okay, so you have to have K in order to make your model, your equation. Alright, and then for B, it says, after how many minutes will there be 1,000 bacteria A cells? So anytime they are asking how many minutes, you know that you're going to have to find what? T, good. Okay, so how many minutes will there be 1,000 bacteria A cells? And one thing we've been talking about with the story problems is I like to find a way to annotate the information I need. Okay, so how many minutes tells me I'm going to find T. And I'm going to do that when, what am I going to plug 1,000 into? Y. So Y is 1,000. Okay, so I'm going to use this model. 1,000 is equal to 20e to the 0.07932t. Okay, and then this process is the exact same that we did here, solving for K. It's just now we're solving for T. Okay, so can you guys go ahead and do the first step? And again, you can decide if you want to simplify this or not. When you cross off the zeros, you have 100 divided by 2. We know that that's what? 50. Okay, so it's less to right if you can simplify it. I'm fine if you leave it like that. And then, of course, once you get E by itself, you take the natural log. So those will undo each other's operations, and then all you'll have to do to solve for T is to divide by the value in front. Okay, I do want you to write the value on this side, 7932. Okay, if you're dividing underneath, you can just go ahead and write that. Okay, and if it doesn't say what to round to for that part, okay, then you can round to the nearest 100. And then will you guys divide that? You say you don't think it's that bad?
So this is what we did.
Yeah, last time it is, yeah. It's just a lot of decimals in a different format, so that can take some getting used to.
I have it in the exact same way you did, but I got it different.
Then you must be missing the parenthesis. Double check that.
Oh, wait, no, it's not.
What'd you forget?
I put the log instead of the.
Oh, okay.
Wait, why would you like? Alright, so she has the exact same.
If it doesn't say, you can choose what to round to.
I was trying to make it. Wait, I want to run the
50.
So we're on the 40.
Oh yeah. No, round to at least the 10th. With the decimals. On your test, I'll tell you what to round to. Hint, hint, wink, wink. I rounded to the nearest 100. Okay. And then for the last one, we're gonna write this in. This is something that's given to you. So bacteria B grows exponentially according to the model, and then they are giving you this model of y equals 52 e to the power of 0.064 t. Okay, so they're telling you that this is the model for this second bacteria. So we were talking about bacteria A. Bacteria B is coming along here. Okay, and then what we have to find for bacteria, for this bacteria, is how many minutes will there be more bacteria A than bacteria B? And that we're going to round to the nearest 10th, it says. Okay, so we have to find T when, let's think about this situation. If there's more bacteria A than bacteria B, then don't we need to set up an inequality? So bacteria A has to be greater than bacteria B. So what we're going to do is we're going to plug in the equation for each. So bacteria A, we found that in part A. And they gave us bacteria B.